In this video, I'll show you how to actually apply the pumping lemma to prove that a language is not regular. And the language I would like to consider is the following. We take all the words over the alphabet A and B such that the amount of A's in the word W is greater than the amount of B's in the word W. And I would like to prove that this language is not regular. Proof is by pumping lemma. Proof using pumping lemma, using the pumping lemma. Pumping lemma is a universal property that all the regular languages possess. So if we can show that this language does not have the pumping property, then we know it cannot be regular. And that's the general structure of the proof. We assume L is regular. If L is regular, then by the pumping lemma there must be a constant P. So then there is a constant P by the pumping lemma. And the idea is that for every word that has at least P characters, it's possible to pump the word to make it bigger or to make it smaller. So there must be some kind of pumping, must be possible. And what we have to do now is that we have to show that if we take a specific word, by pumping we get out of the language. So the first creative thing you have to do is find a suitable word. Usually the easiest is to somehow put the P inside the pattern here. It's not that easy to see what kind of pattern might be useful. Let's think of a simple word. There are more A's in W than B's. So we can just put the A's in the front and the B's behind. So we might consider the following. Word, let Z be A to the power of P plus 1, B to the power of P. So we have P plus 1 A's followed by P B's in this word. So this word is for sure in the language L because the amount of A's is really greater than the amount of B's, so it's in. And the size of the word is greater or equal to P, so it's a suitable word for the pumping lemma. So we take this word, and if we have this word, we know that by the pumping lemma it's possible to divide it in three parts. Then Z equals U V W. So we can split it up into three parts such that the first part, UV, has a size less or equal to P. If the size is less or equal to P, then we know that the first part can only consist of A's because the first P plus 1 letters in the word Z are only A's. So if we have a look at the first letters up to P, there are only A's. So we know that UV has only A's. And that's the general trick. We may choose the word Z, but we may not choose the decomposition in UVW. So we have to make the word so specific that we can derive some knowledge about the decomposition. And what we can derive is actually that UV consists only of A's. Then UV consists only of A's. if uv consists only of a's, then v consists only of a's because it's a subword. So then v consists only of a's, and then I can somehow say, well, if there are only a's inside, it must have the form v equals a to the power of, let's say, k for some k from the natural numbers. We don't know the exact number k, but there must be a k. We cannot fix it, but we know that there must be a number k. So v as a to the power of k. Now, we can either increase the number of occurrences of v in the word, or we can decrease it by 1. And it's, in this case, the only possibility is decreasing the amount of a's in the word. So consider the word u v to the power of 0 w, which is the same as uw. Uw is the word that you get if you take this word, z, and you remove v. So v is no longer inside, so we have removed k a's. So they are gone. The remaining number of a's is a to the power of p plus 1 minus k b to the power of p. We also know that k cannot be 0, because v may not be the empty word. So we know that k is not 0. No. So furthermore, k doesn't equal 0. So if k doesn't equal 0, and we have a look at this word here, we know that this cannot be in the language, because the amount of a's is no longer greater than the amount of b's, because we have removed at least one a. So there are not more a's than b's in the word anymore. So the resulting word is not in L. So then u v to the power of 0v is not in L. And this is actually a contradiction to the pumping lemma. So this is a contradiction to the pumping lemma. And we can conclude that the assumption was false and that the language is actually not regular. So the assumption was false. L is not regular. And that concludes the proof.